In other videos, we discussed the two independent samples t-test, which is used when you have two different samples and the individuals within each sample are independent of each other. There's no direct one-to-one connection between people in one sample and people in the other sample. In fact, you don't even have to have the same number of people in each sample. But there are also situations where the samples are not independent. There is some sort of a direct connection between one person in one sample and one and only one person in the other sample. A common example of this is a pre-test, post-test study where a single sample of participants are assessed at a pre-test and then take part in some intervention or program, after which they complete a post-test assessment. Now, in those types of situations, you can ignore this one-to-one connection between an individual in the two samples and analyze the data using a two independent sample t-test. But there's a better way, a paired sample t-test. In these videos, we'll use hypothetical pre- and post-test data on 6 people to illustrate the strength of a paired sample t-test. But to do that, let's first examine the same data using the old reliable two independent sample t-test, okay? Now, for this hypothetical example, we want to see whether an intervention can reduce the level of math anxiety based on a sample of 6 students. Each student has a pre-test anxiety score before the intervention, and they have a post-test anxiety score after the intervention. We'll use an alpha of 0.05 and a non-directional two-tailed test, right? Now, to save time, we'll just focus on calculating the t-scores and the p-values and see how they change and how our decision to reject or fail to reject the null changes based on whether we do an independent sample t-test or a paired t-test. Okay, so let's get started and with our pre-test scores. Here are the anxiety levels for the 6 students prior to taking part in the intervention, right? And if we add these up, right, what do we see? We add them up, calculate, divide by the 6, we get an average of 7, right? That's the mean for the students on their pretest, right? Then here are the post-test anxiety levels for those same 6 students after they took part in the program, right? Our n is still 6, right? So if we add those up and calculate the mean, we get a mean of 5 for the post-test. Okay, pretty straightforward. Now, the means are different, but are they so different that we're convinced the means in that population of students who could get the intervention are different from the population of students if they don't get the intervention? Or is it just random sampling error? Now, remember, for now, we're going to ignore the fact that it's the same students in both of those samples getting the pre and post test, and instead treat them as 2 completely independent samples. So let's calculate an independent sample t-test using our alpha of 0.05 as that criteria whether we're going to reject the null hypothesis or fail to reject the null hypothesis, right? And the null hypothesis, again, is that the means in the populations of those getting or not getting the intervention, those means in the population are the same. Okay, now for the 2 independent sample t-test, t is equal to x bar 1, x sub 1, x this mean for sample 1, minus x bar 2, the mean for sample 2, divided by the standard error of the difference in means. And the standard error for the difference in means is equal to the pooled standard deviation times the square root of 1 over n1, the sample size for the first sample, and plus 1 over n2, the sample size for the second sample. And the pooled standard deviation, right, where we're pooling across the two samples, is equal to the square root of n minus 1 times the variance for sample 1 plus n2 minus 1 times the variance for sample 2, all of that divided by n, the sample size for sample 1, n1 plus n2, the sample size for sample 2, minus 2. Okay? So now what's interesting is mathematically that n1 minus the variances in the numerator, those are both equal to the corresponding sample sums of squares. But in fact, we typically don't know the sample sum of squares, so we use the variance, we do this using the variance instead. But if we do know the sample sum of squares, we can simplify this by just plugging in the sum of squares for sample 1 plus the sum of squares for sample 2 divided by n1 plus n2 minus 2. Right? Now in this case, being we're going to do the calculations by hand, we will calculate the sum of squares. So we can go straight to this formula and save ourselves a few steps, okay? So let's calculate the sum of squares for the pretest and the post-test samples, right? So going back to our pretest scores, right, we subtract the mean from each person's score to calculate the deviations from the mean. So that first score is 4, the mean is 7, so that's 4 minus 7, or negative 3. We then do that for each of the other 5 scores to get negative 1, 0, negative 1, positive 2, and positive 3, right? Those are our deviation scores. We then square those deviation scores to get our squared deviations and add them up. So negative 3 squared is 9. We keep going. Negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 2, 3 squared is 3. We add that all up to get our sum of squares for the pretest scores, which is 24. 9 plus 1 plus 1 plus 4 plus 9 with a 0 in there is 24. So that's our sum of squares for the pretest. Great. Okay, now let's do the post-test scores. We calculate the deviations from the mean by subtracting the mean, which is 5, from each score, right? So then those are our deviations. We then square those deviations, right? So negative 3 squared is 9, on and on and on. Those are our squared deviations. We then add up the squared deviations to get the sum of squares for the second sample, our post-test scores, which is 22. Great. So we got our 2 sum of squares. Okay, we'll keep going now. So let's plug those values in to get our pooled standard deviation. So here's our pooled standard deviation formula. I got to get my pointing straight. Nope, it's this way. There, down there. The pooled standard deviation is the square root of the sum of squares for sample 1 plus the sum of squares for sample 2 divided by n1 plus n2 minus 2. We're going to then use this pooled standard deviation formula to calculate the standard error of the mean, the standard error of the difference in means, correct myself there, which we then plug into our t formula, right? So we plug them in. We put in our our sum of squares of 24 plus 22, right? So that's 24 plus 22 divided by the sample size n1 plus n2 minus 2, so that's 6 plus 6 minus 2, right? That gives us 46 over 10, the square root of that. So 46 over 10 is 4.6, so we want the square root of 4.6, which is 2.145. That's our pooled standard deviation. Okay. Now we take the pooled standard deviation and we're going to plug that 2.145 up into the standard error of the mean formula. So if we plug that in there, we get the standard error of the difference in means, that's standard error of the difference in means, is equal to 2.145 times the square root of 1 over n1 plus 1 over n2. All right, so we plug in our n's. That's the square root of 1 over 6 plus 1 over 6. Well, 1 over 6 plus 1 over 6 is 1/3, or 0.333. So the square root of 0.333 is 0.577. If we multiply 2.145 times 0.577, we get 1.238. That's our standard error of the difference in means. We then, at this point, we're ready to calculate our t-score. We take our standard error of the difference in means, and we're going to plug it into the t formula. And our t formula, x bar 1 minus x bar 2 divided by the standard error of the difference in means. So our mean for sample 1 was 7, and our mean for sample 2 is 5. Great. If we do that, that gives us a difference in between the two means of 2 in our numerator. That's how big of a difference did we see. Our denominator is the standard error of the difference in means, which we just saw was 1.238. If 2 divided by 1.238 gives us a t-score of 1.615. We're almost there. Okay, now just need the degrees of freedom, and the degrees of freedom is equal to n1 plus n2 minus 2, which is 6 plus 6 minus 2, or 10 degrees of freedom. Great. So let's kind of write up the results in that sense. Our t, right, with 10 degrees of freedom in parentheses is equal to 1.615. If we look that up with a calculator, we see that our p-value is 0.1374. Remember, that's the two-tailed p-value for both tails. And 0.1374 is larger than our alpha level at 0.05. Our p is greater than our alpha level, so we are going to have to fail to reject the null hypothesis. The data don't allow us to conclude that there's any effect for the program. Ouch! But don't give up hope. This is what can happen when you make the wrong choice for a statistical test.
He chose poorly.
Oh, okay. It could be worse, but fortunately, there is a better way. We'll cover that in the next video, all right? Bye for now.